Hi guys, in today's video we're going to be focusing on ideal gases. So in the last video we talked about the three main gas laws and an equation that concerned those gas laws. So those gas laws apply to gases that are ideal. So what exactly is an ideal gas? Now ideal gases have some basic assumptions. Now the first one is that the gas molecules are going to have negligible volume compared to the total volume of the gas. Now when we use the phrase total volume of the gas, what we're mainly referring to is the volume of the container that the gas is in. And this point over here is one of the most important points that's here. So I'm just going to put a star on it. And examples of these points in detail with calculations are there in the introduction to gas laws videos. So you can check that out if you're confused about it. The second point is that there are going to be no intermolecular forces between particles. So if you have this container over here, which has all these gas molecules, according to this law, there are going to be no intermolecular forces between all of these particles inside this container. The next point that we have over here is that collisions are perfectly elastic. What that means is that when these two particles collide with each other, when any other particles collide with each other, there's going to be no loss in energy. The collisions are going to be perfectly elastic. The next assumption that's there is that the particles are going to be in constant random motion. And after that, the assumption that we have is that the pressure that's exerted inside this container over here, inside any other container containing a gas, is going to be due entirely due to collisions between the molecules and the walls of the container. Now we're going to be discussing real gases and ideal gases. So in the previous slide, we discussed the assumptions of an ideal gas. Now, the gases that we see, like nitrogen, hydrogen, carbon dioxide, oxygen, these are real gases. So the behavior they exhibit is not exactly the behavior that's exhibited by ideal gases, right? So what we're going to be discussing right now are real gases. So right now, why normal gases like oxygen, nitrogen, or any other gas is not considered to be an ideal gas? So the main reason behind that is that the two main assumptions, the first two that I put stars on, are not met by real gases. In real gases, the particles are going to have a certain volume and they're going to have a certain size. And because of that, they're going to have a significant amount of intermolecular forces between them. So the forces between them are not going to be negligible. So when is a real gas most like an ideal gas? Now some gases are more ideal, some gases are less ideal. So now we're going to discuss what exactly makes some sort of a gas ideal and when is it going to be like an ideal gas, under what specific conditions. So the first condition that we have is high temperatures. So when the temperature of any gas increases, the kinetic energy of the molecules is going to increase. Because of that, the molecules are going to move further away from each other and the intermolecular forces are going to break. Now, if you remember from the previous slide, one of the assumptions of an ideal gas was that there's going to be negligible intermolecular forces between them, between the particles. So because of that, at high temperatures, a real gas becomes more like an ideal gas. The next condition that we have is at low pressure. So at low pressure, what's going to happen is the total volume increases. If you remember Boyle's law, you'll know that pressure is inversely related to volume. So when you decrease the pressure, the total volume of the gas, and like we talked about previously, total volume refers to the volume of your container. The particles themselves, which have a fixed volume, are going to have a negligible volume compared to the volume of the container, which satisfies the first assumption that we discussed. So at these two conditions, high temperature and low pressure, a real gas will be most like an ideal gas. Now, when is a real gas not like an ideal gas? So this is going to be at low temperatures, when there's going to be less kinetic energy and more intermolecular forces, and at higher pressures, when the total volume is going to decrease. So the particles are going to have a significant volume compared to the total volume of the container. Now we're going to be taking a look at a few examples of real gases that we see around us: carbon dioxide, nitrogen, ammonia, neon, all these gases. And under what conditions are they ideal, and which we're going to compare them to each other as well. So we're just going to be looking at a few examples. So this line over here, this white line, refers to an ideal gas. Remember when we discussed that pressure is inversely related to volume? So PV is equals to K. And we made a graph in which if you plot PV against P, it's going to be a completely horizontal line. Now, this is true for ideal gases, not for real gases. So, for real gases, it's going to deviate, right? So, now you have two graphs for carbon dioxide. One is blue, one is yellow. The blue one is going to be for carbon dioxide, which is at low pressure. As you can see, the pressure values over here are considerably lower than the pressure values over here. And the yellow one is going to be carbon dioxide at a high pressure. As you can see, this gas deviates a lot more from this straight line than the blue one over there. And that is because at low pressure, carbon dioxide, or any other gas for that matter, is going to be more ideal. Now, it won't be exactly ideal because no gas can be exactly ideal, but it's going to be close. Now, let's take a look at another factor, which is temperature. Now, in this case, at lower temperatures, as you can see, this graph over here is going to be less horizontal. And this graph over here is more horizontal, right? So the condition for having an ideal gas is that K over here needs to be a constant, right? So when you plot PV, it has to be a straight line. Now at higher temperatures, this thing over here becomes more and more like an ideal, becomes more and more like a straight line. So that shows you that as you increase your temperature values, nitrogen or any other gas is going to become more ideal, and we have the reason for that before. Now let's look at a question. So the question is, place the following gases in decreasing order of ideal behavior. So for the examples, we have ammonia, neon, and nitrogen, right? So if you put these in order, you're going to get neon, nitrogen, and ammonia. Now, why is nitrogen going to be after ammonia? Why is it going to be less ideal? The reason for that is nitrogen has stronger ID-ID forces as compared to neon. So because of that, it has a significant amount of intermolecular forces, which goes against one of the ideal gas assumptions. And ammonia has the strongest intermolecular forces out of all of them. It has hydrogen bonds. Now, if you're confused about hydrogen bonds, there's a video on that in the bonding chapter, so you can go check that out. But just for the purpose of this chapter, hydrogen bonds are the strongest form of intermolecular forces that you can have. So this is why ammonia is going to be the least ideal, because it has the strongest intermolecular forces.